Okay, in this video, let me do a few things. First, I'm going to give more examples about horizontal stretch and compression for graphs of y equal to f of 2x or 3x, whatever. This number 2 is not important. Okay, so this is a horizontal stretch. In order to make the problem clear or simple, let's select this y equal to fx equal to x squared, okay? X squared has, maybe x cubed. I don't know if we mentioned this before. Let's use x cubed. I need longer. X cubed, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Okay, let's divide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 10. 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17. Okay, so we just draw the coordinate system. And the graph of x cubed, remember in that library of the functions, we had it. When x is 1, it's 1. When x is 2, it's 8. So 1, 2, 3, 4, 5, 6, 7, 8. It's 8 here. When x is 3, it's already 27, which I couldn't sketch it, plot it. So, but anyway, it's very tall. When x is negative 1, negative 1 cubed is negative 1. When x is negative 2, negative 2 cubed is negative 8. Negative 8 is here. And when x is negative 3, it will be negative 27. It's very low. So anyway, so it's like this. Now let's see how do we sketch the y equal to 2x. Wow, 2x. Let's check. We will select several points in order to see the idea. When x is 0, so 2x is 2x, when x is 0, 2x is 0, 0 cubed is 0. When x is 1, 2x is 2, 2 cubed is 8. When x is 2, it's already 4. It's 4. 4 cube, 4 cube, what's 4 cube? 4 cube is 64. It's 64. Okay, now let's check. It's too big, so I'm going to select some smaller number. When x is 1/2, 1/2, x is 1/2 times 2 is 1. 1 cubed is 1. So let's check. 1/2 is here. When x is 1/2, y is 1. When x is 0, y is 0, so this is the point. When x is 1, it's already 8, so it's here. So if you sketch the f of 2x, here the similar one. No, it's bigger. So you kind of compress it. See here, you compress. It's a horizontal compress. You push. This is y-axis. This is a y-axis. You push this curve close to the y-axis. So that's a horizontal compression. Here's the similar thing. You push this this curve towards the y-axis. You also push this curve towards the y-axis. Okay, so you put this way, this horizontal squeeze, and that's a squeeze. Let's check another one. Cubed. As if we have a 1/2, if we have 1/2 here, then let's check. 1x is 0. 1/2 times 0 is 0. Cubed is still 0. 1x is 1. 1/2 times 1 is 1. This is 1. When x is 1, you got 1/2. 1/2 cubed is 1/8. When x is 2, 2 times 1/2 is 1. Cubed is 1. Okay, so now let's check. When x is 0 is 0 here, this point. When x is 1, it's 1/8. It's very low here. When x is 2, the value is equal to 1. It's here. When x is 3, x is 4. Let's check x is 4. When x is 4, 4 times 1/2 is 2. 2 cubed is 8. So 1, 2, 3, 4. At 4 is here. So if we connect them, it's this way. Okay, so here's a similar thing. You kind of you see, when you fix this y-axis, the original curve, you stretch it away from the y-axis. This is a horizontal stretch. Okay, so I hope this example make this horizontal stretch better. But anyway, you still need to do some sample point and determine some basic sample point, and then you get the sketch. It's not just randomly. Okay, it's a stretch, so you just draw it away from the further away from the from y-axis. We don't do that. We still need some sample plot. But the argument is that once you know the graph of f of x, when you have a coefficient, you more or less get the big picture of the graph. It will be like this, or it's a circle, it's a straight line. It will be more or less like that. But the horizontal property or the vertical property are modified by these coefficients. Okay, so you still need this. When you have a 1, 2, 3, 4 points. When you have the 4 points, you can just get the stuff, get the graph. Okay, so this is a example about the horizontal stretch and compression. Let's see next. Next, some student asked the problem in section 3.6, 10 and 11. Okay. In section 3.6, 10 and 11, on page 261, problem 10 says you have a square. Inside the square, you draw a circle inscribed in the square. This radius is r. Okay, so a circle of radius r is inscribed in a square. And A express the area A of the square as a function of the radius r of the circle. Okay, so in order to find the area of the square, you need the side, the length of the side. This, if you check it, is exactly the diameter, twice of the radius. So the side of the square is 2a, so the area is 2a squared, which is 4, not 2a, 2r squared, which is a 4r squared. Okay, so that's part A. Part B, express the perimeter P of no, I read, yeah, express the perimeter P of the square, yes, that's right, of the square as a function of r, as a function of r. Perimeter of the square, well, this side is r, so the P is 4 times 2r is 8r. So this is a perimeter. This is a problem 10. Let me make sure this is a question the student asked. Okay, so check. Yes, question 10, 11 from section 3.6. Okay, that's correct. This is question 10. So the answer will be area is 4r squared. Perimeter is 8r. 11. 11. A wire 10 meters long is to be cut into 2 pieces. One piece will be shaped as a square. And the other piece will be shaped as a circle. Okay, so we have a wire. We cut it into 2 pieces, and this part we make it a square. The whole thing is 10 meters long. And we assume this the side of the square is x. And now we have the circle. Okay, So this square has side x, so you have x, x, x. So the total perimeter is 4x. So this piece is going to be 4x. Then the other part will be 10 minus 4x. Right? So this is suggested in the graph. Okay, that's a setting. This is a setting. Now let's see the question. Question: express the total area A enclosed. Okay. Express the total area. Total area A enclosed by the pieces of wire as a function of the length x of a side of the square. Okay, anyway, let me still use the pen, ball pen. Okay, let's check here. For the square has area x squared. Okay, so this one is clear. The thing is, what is the area of the circle? Circle, assume the radius is r. So here, assume the radius of the circle is r. Then this 10 minus 4x is a perimeter. Okay, so 10 minus 4x is a perimeter. Perimeter of the circle is a 2 pi r. So perimeter of the circle is a 2 pi r. It is also equal to 10 minus 4x because we use this wire to bend a circle. Okay, so from here we can solve. We divide this equation by 2 pi. We get r equal to 10 minus 4x over 2 pi. If you cancel 2, you will get r is a 5 minus 2x over pi. Why do we need r? Because we are looking for the area of the disk, area of the region enclosed by the circle. Okay, so the area of the region enclosed by the circle is pi r squared. We need everything in terms of x, so we cannot just put r here. We cannot leave pi r squared as the answer. We have to use x. So pi r squared, so it's a pi, this whole thing, 5 minus 2x over pi squared. So it's a numerator squared and denominator squared. You have pi times, and denominator you have a pi squared. You cancel 1 pi, you get just 5 minus 2x squared over pi. You cancel 1 pi. Okay, so this is the area of the disk. The total area is total area. A equal to x squared. That's the area of the square plus 5 minus 2x squared over pi. Okay? So this is the first one. And second, the domain of A. What is the domain of A? The domain of A is based on the question. So you cut it into two parts. so you have two parts. The 4x is greater than, the 4x is greater than 0. So you have 4x greater than 0. You also have 10 minus 4x greater than 0, right? Two parts. The top part is really a wire. The bottom part is really a wire. That's the only requirement. Once you get those two segments, you can construct a square and a circle. So 4x greater than 0, x greater than 4. 10 minus 4x greater than 0. So 10 is greater than 4x, then x is less than 5 over 2. Sorry, how do I get 4? I'm so stupid. I'm sorry. X is greater than 0. Okay. So x greater than 0 from the first part, x less than 5 over 2 from second part. So the domain is between 0 and 5 over 2. The domain of area function is between 0 and 5 over 2, just because we need two pieces. So you have pieces is greater than 0, right? Okay, so this is a domain, not greater than 4, greater than 0. Well, sometimes I make mistake. Well, almost every time. It's bad. Okay, so this is a problem 10. Problem 11. This is a problem 11 in the section 3.6. Okay. Another thing is that again, I was pointed out a mistake in the section in the video of section 3.5 part 2 around 34 minutes 20 seconds. In the problem, I did the reflection about the y-axis. The reflection should be about y-axis, not x-axis. But I wrote x-axis in the third requirement. That was wrong. Okay? So I did want to do the reflection about the y-axis. So that's why I get negative x instead of x. Okay? Okay? So it should be y-axis, not x-axis. That's my mistake. I wrote it wrong. Let's see. Another thing. It's about the let me find it. It's an exercise on page 242, problem 39 and 40. Fx is two integer function of x, and 40 is fx is integer of 2x. Okay. This one is the vertical stretch. Vertical stretch with coefficient 2. This is a horizontal compression with coefficient 2. Okay, so let's try it. First, what is the integer function? Integer function, I guess for some of you, it's the first time to get this concept. The graph of the integer function is an infinite stair or infinite step function graph. Okay, infinite step function. This is a fx y equal to integer of x. Now let's try to graph 2 integer x. 2 integer x is not that bad. 2 integer x, you just stretch it along the y direction. You don't change anything about x. You still do everything in the parallel way. Okay, so you just draw it in the same pattern. You got 1, 2, 3, 1, 2, and 3. 1, 2, 3, 4, possibly 5, 6. We need more. 6. Okay. 1, 2, 3, 4, 5, 6. Let's check. When x is 0. When x is 0. When you have 1/2, it's still 0. When you have 8/9, it's still 0. So this part is not changed. Times 2 does not change 0, right? So for this term, if it's on the x-axis, the y value is 0, times 2 is still 0. The thing changes for 1. If you have x equal to 1, integer of 1 is 1, times 2, it becomes 2. So this horizontal line, you see here, it is vertically stretched up. You multiply the value by 2. And here's a 4. You check 2. 2 is stretched up to 4. And you will have 6. Here is a similar thing. This is -1, -2. So when you get x equal to -1, when x is -1, integer part of -1 is -1, but times 2 is -2. So this point is here. 3, 4, -3, -4, sorry, negative. There's no such part. Okay, so that's a vertical stretch. In the stretch and compression part, vertical one is not the problem. The problem is a horizontal stretch and the compression. Okay, so just make it longer. Now let's check the horizontal stretch. Horizontal stretch requires a little bit explanation. Okay, now let's check the horizontal stretch. Okay, so 1, 2, 3, 4. Let's say 4. How do we determine the horizontal stretch? And in other words, how do we pick up the sample point? We are going to pick up the sample point x so that with this coefficient, you reach the changing point. Okay, so what I mean is this. So here's 0. You see here, 0. At 0, in the left part is lower, in the right part is higher. So 0 is a changing point. There's a jump. We say there's a jump. So we want to get 0. How do we get 0 from 2x? Then x is 0. X is 0, 2x is 0. Then you get f of 0 is integer part of 0 is 0. So 0 is still here. And then we need 2x equal to 1 because at one part you have a change. 2x is equal to 1, x is 1/2. So you're looking for 1/2. Fx is integer of 2x, so this f is evaluated at 1/2. It is 1. So at 1/2, it becomes 1. And then you move to number 2. 2x is number 2, then x is 1. Then f of 1. This input corresponds to the x. This input corresponds to x. Not corresponds to this part. This part are from the original stuff. Okay, so this integer part of 2, you get 2. Okay, so now I'm going to do the following thing. Between them, you see between between 0 and 1, what you see, you just push it towards the y-axis. This is horizontal, so this part is still horizontal. X is 1, it's 2, so here. So between 1 half and 1 is also horizontal. And now possibly you see the pattern. You actually squeeze it. Here each segment has length 1. When you get horizontal compression, the length becomes 1/2. Divide by 2, you get 1/2. So that's why here you get 1/2, 1, this is a 3/2, 2, then this is a 5/2, and a 3, stuff like this. And those 1/2, 1, 3/2, 2, 5/2, 3, they are from they're actually from the solution of a 2x equal to 0, equal to 1, equal to 2, equal to 3, equal to 4. We are interested in the jumping point or the changing point. If between them nothing changes, you just get the smooth modification, compression of stuff. The previous example, the first example, there's no changing point. When there's no changing point, you just pick up the simple. Here you see, you just pick up the simple value, which you can evaluate, and get some control point. Then this part, it's really up to you. But for this cube function, if you select a bigger number, it's out of your space. So you will all possibly just select the 0, 1, 2 stuff. Okay? So when there is no jumping point or the breaking point, you you properly select the point so that you can easily evaluate. You do not give yourself a trouble. So you easily evaluate. You don't put like 1/2 here, not 1/2. You don't like to put pi here. If you put pi here, you don't know what is a pi cubed. Okay? So just pick up simple point. And here, there's a break. When there's a break, you clearly will try to determine the behavior of the function at the break, jumping point or the break point. Okay? So this is, again, the step function, but with a narrow step. And this vertical distance does not change. Here, the vertical distance is still 1. But in the vertical compression part, this vertical change becomes 2 because you multiply it by 2. Here, this one, you multiply by 2. Okay? So the graph of the function looks like this. Okay? That is the explanation. I hope this make the problem clear. But anyway, if you have question or you figure out my mistake in the video, just let me know. I appreciate whatever you point out. Even you think, even you give me the wrong conclusion, it's still fine. I'm happy to discuss whatever conclusion with you. Okay? Thank you very much. Okay, I will put this on YouTube soon, quickly.